another classes. One more minute to get started. Okay, how long?
Hopefully I'll be done around 11:45 or 11:50.
Oh, yeah.
I have to teach right after. Yeah. Yeah, that's basically that's the program that's funded it is not the CPS program, but it's
Okay, I think we probably should get started because in the interest of time, right after this class, there's another class that's coming in. And also Sammy's going to be with another class right after this. So I think let's get started. So let me introduce about the Sam Coogan. I think Dr. Sam Coogan is currently a professor, an assistant professor at Georgia Tech. He has also a joint appointment between the ECE as well as the civil engineering. So it's quite kind of promising. It's an area that kind of both of them, so you probably can take advantage of the current research that he's going to talk about. And he got his bachelor degree from Georgia Tech from ECE, and later on he got his master and the PhD degree from UC Berkeley, and he has been joining the assistant professor at UCLA in ECE since from 2015 to 2017. So he started joining the Georgia Tech in 2017. And a specific thing that I think I just wanted to say that he is quite doing a lot of work in the area of the specific autonomous transportation system. That is the one kind of linking between as well as transportation. And one thing I just want to mention that Sam has received a NSF Career Award, which is quite prestigious from NSF last year in this area. So I think he's going to be shared with us in terms of that area and as well as research. So with that, please join me.
So yeah, as Gene said, I've been here for about a year and a half, and it's great to be able to give this talk in this lecture series. The title of my talk is Routing and Traffic Networks with Mixed Autonomy. So before we kind of dive into the details, let me just give a little bit of overview about what I do, since I do have this sort of strange joint appointments in electrical engineering and civil engineering. So my research is largely in the area of control theory applied to transportation. So my background is in an area of electrical engineering called control theory, concerned with sort of all aspects of or various aspects of controlling transportation networks. So here's sort of, I just kind of want to highlight four of the kind of thrusts in my research group right now. So this first thrust in the upper left, this is what I'm going to talk about today in this talk. This is this idea of studying what happens when we have autonomous vehicles on our roads and understanding how they're going to affect things like routing behavior, delays, and what we can do about it if we need to change things and make adjustments, either through tolling or through traffic control measures, things like this. So this will be kind of the focus of my talk today, and I'll sort of walk us through some particular aspects of this. The second kind of research thrust that I focus a lot on is this, what I call correct by design flow networks. So in this research thrust, I'm pulling in tools from something called formal methods theory in computer science. These are tools originally designed for verifying and validating software and hardware systems, making sure you don't get faults in your software systems, making sure you don't have infinite loops. And we're applying a lot of those tools to cyber-physical systems, things that have physical components moving in the physical world. And it takes quite a bit of effort to get those tools to kind of work in those domains, and so a lot of our research focuses on that. We do a little bit of low-level control, and I use low-level in the sense that we're talking about controlling individual vehicles. So this is a project that's being sponsored by Ford right now, where we're looking at developing algorithms for autonomous vehicles in what we're calling unstructured environments. So people have a pretty good sense these days of how to develop algorithms for, say, adaptive cruise control on a freeway lane and pretty well-defined traffic conditions. But when we kind of talk about these more unstructured environments, parking lots, roundabouts, things like this, it becomes much more difficult to kind of codify rules you can want on the road. A lot of it, when you do it yourself, is via eye contact and human interaction. So finding a way to do this autonomously is something we're looking at. And then I do have some sort of work that I collaborate with a faculty member in the School of Public Policy, and we're looking at pricing algorithms for electric vehicles. So we're trying to understand how the electric vehicles interact with our power infrastructure and make decisions there. But like I said, today I'm going to focus largely on this upper left quadrant here, studying mixed autonomy in traffic. So here's kind of the high-level question. There are many routes between any origin and destination in a large traffic network, right? So here's the city of Atlanta. If you want to get from, say, Georgia Tech up to Marietta, there's at least a few different routes, or you can take a few different freeways. You can take 41, stay off the freeway, right? So you have lots of different options about how to get from point A to point B. And then you ask yourself, we as researchers ask ourselves, how do drivers make these decisions, right? Well, in some sense, it's obvious, right? Drivers, either through experience or through looking on Google, they're going to choose the route that is the shortest route, right? Sometimes people choose routes for other reasons. It's a little bit easier to drive, maybe not on the freeway, or maybe it's easier to drive on the freeway. You need to stop by something on the way. But by and large, a good modeling assumption is that people choose shortest routes. Okay. So it's a simple sort of assumption to make. It's a simple thing to postulate, but it has sort of important ramifications when we want to understand how we should design traffic networks, how we should study them, and what kind of behavior we expect in these traffic networks. And a lot of this is going to change when we have mixed autonomy scenarios, where we have some autonomous vehicles interacting with regular vehicles on our roads, and so we want to understand how to study those types of networks. So here's my talk outline. I'm going to present a fairly rigorous but standard mathematical model for how we would model routing between origins and destinations in a traffic network. I'm going to talk about equilibrium flows versus optimal flows in each system. So I'm going to talk about what people do when they encounter traffic networks and what we would prefer them to do as traffic planners and traffic designers. I'm going to talk about something called the price of anarchy, which is kind of a fun name for a specific mathematical metric that characterizes this difference between an equilibrium flow and an optimal flow. And to be honest, these first three bullets are all going to be known results. They're not going to have to do, they're not research results for myself, they're kind of well-known results in the routing game literature. But then the last part of my talk, I'm going to talk about how we've been building on these results in the mixed autonomy framework. And this is where I'm going to just kind of talk a little bit about my research results at the end. Okay. So the mathematical tool we need to understand these routing problems, to understand how people move from point A to point B, is something called non-atomic selfish routing games. So that's what we're going to study, and if you Google that, you can find Wikipedia pages on this and find textbooks about it. I want to unpack this, and I want to sort of describe what each of these four words mean in our context and the types of assumptions we're making. So the first is this idea that we're talking about non-atomic routing networks. Okay? So what that means from a physical perspective is that no single vehicle is changing the route delay between origin and destination. When you decide to travel from point A to point B, your car on the road doesn't materially impact the delay. Of course, it's an approximation. You do make it slightly longer for maybe the person behind you by a few seconds. But by and large, you individually don't have an impact on delay in traffic networks, right? But somehow in aggregate, we all do impact delay, right? When we're all on the road, we're all doing this together, we have sort of an impact on delay. So even though delay does depend on sort of aggregate flows, it doesn't depend on individual vehicles. That's where the word non-atomic comes from. The selfish part comes from the fact that we're thinking of each of these drivers as being selfish. They're looking for the shortest route. It's a routing game. So the only decision drivers get to make is which route they're going to take from point A to point B. They're not making a decision about what time they're leaving. They're not making a decision about which origins and destinations they're going to. They're just making a decision about which routes they're going to take to get between A and B. And then it's a game. Agents are focused on themselves. They care about themselves, getting from point A to point B. They don't care about your neighbors, right? So kind of pack all this together and we can get a pretty precise mathematical formulation for what types of problems we're interested in studying here. Okay, so let's set this up. I try to keep the math notation as light as possible since it's lunch and people are busy eating and things like this, but we'll need a little bit. So we take a pretty abstract view in this work when we talk about traffic networks, and traffic networks are just a series of points connected by links, okay? So they're intersections connected by roads, they're neighborhoods connected by paths, things like this. And the basic premise is the following. We have a fixed volume of vehicles between any pair of origins and destinations. Okay, so there's a fixed number of vehicles, say 1,000, that are trying to get from, say, node A to node C. All right? Based on the network topology, an OD pair can have multiple paths. So for example, to get from A to C, you could take node A to node B to node C, or you could go A, E, D to C, right? So this has at least 2 paths between A and C. Actually, there's 3 paths between A and C. And then the other sort of mathematical ingredient we'll need for this is we'll have a delay function for each edge. Okay, we'll call that cost. So really, it's the delay of taking a particular edge to that driver. And this delay is a function of how many other people are taking this link, right? So there's a flow on that link. That's the number of vehicles taking that link. And the cost that a vehicle experiences depends on that total flow, okay? We'll do some examples on the next slide. And the game is we want to decide all of the flows in the network so that people get from their origins to their destinations, right? That's the objective, okay? So let's do an example. So suppose we have 1,000 vehicles that need to travel from point A to point C in this network, okay? And there are 3 routes for doing that. They can go A to B to C, they can go A, E, D to C, or they can go A, B, D to C, okay? And just for the sake of illustration, let's suppose we have a couple cost functions. Let's suppose that for links 1, 2, and 3, the cost is just FE, so the cost for that link is just the number of vehicles that take that, okay? And you can put units on this and try to convert vehicles to dollars and things like that, but let's just keep it simple and keep the math easy, right? So if 100 vehicles are on link 1, we'll say it costs 100 units of time to vehicles on E1, okay? And then let's just suppose that for the other 3 links, 4, 5, and 6, the cost is actually twice as many people are on that. Maybe there's only 1 lane on these roads and 2 lanes on these roads or something like that, right? So here's one possible way we could solve this problem and distribute the 1,000 vehicles on these links. We could put, say, 800 vehicles on link 1, 200 vehicles on link, let's see, right? 800 on link 1, yeah, 200 on link 3, 600 on link 2, 200 on link 6, 200 on link 4, and 400 on link 5, something like this, right? If you check that, they sum up correctly, and the number of vehicles coming in should be the number of vehicles going out, and we've accounted for all 1,000 vehicles trying to get from A to C. Okay? And then, just to kind of illustrate this, if you were trying to compute the cost, there's a cost associated with each of these 3 routes. So let's just compute one of these costs. Let's compute the route for the cost for route A, E, D, C. So there's a total of 3 links involved there. There's links 3, 4, and 5. 200 vehicles are on link 3. The cost for each of those vehicles is just 200 because this is the cost of link 3. So we have 200, and then there's 200 vehicles on link 4, but the cost on that link on that road is double. So we have 2 times 200. And we have 400 vehicles on link 5, and that cost is 2 times 400, and I think that sums to 1,400. Okay, so every single vehicle that takes route A, E, D, C is experiencing a delay of 1,400 something, maybe seconds. That's what we have. Okay. So again, the delay depends on the total flows involved, right? But if you remove any one vehicle, they really have negligible impact on that individual flow, right? Any questions on kind of the mathematical setup we're dealing with here? Good. Okay, but then you should ask yourself, okay, so sure, that is a one way to split the flows. That's one way to account for all 1,000 of these vehicles. But then we should ask ourselves, is this a good flow? Okay. And the answer to that question depends on who's asking, right? If you ask the driver, they're going to say, well, was there a route from my origin to my destination that had a better cost? If there was a route, then I'm kind of unhappy and I would prefer to choose that route, and I'm not happy with this flow, right? If every driver asks this question and the answer is no, then those drivers are going to say, all right, I'm happy with where I ended up on this network, And if that's the case, we call this a user or wardrop equilibrium flow. Okay? But now if you turn around and ask a traffic planner, are you happy with the flows that we've decided for this network? They're going to ask a completely different question, right? They're going to generally be like, okay, I don't actually care about this individual person or that individual person. I care about the network in aggregate, right? So I want to know, is the total cost to all drivers in the network reduced, right? And so if you can't come up with a flow that reduces the total cost in the entire network, we call this a system optimal flow, right? And sort of the very important piece here, the part that kind of underlines this routing flow theory, is that there can be a gap between ward drop and system optimal, right? Okay. So let me introduce some formal definitions now, just so we can kind of wrap our minds around this. So we say that a set of edge flows for each edge in the network, we call it a user or ward drop equilibrium. If the total per driver cost for any possible routes between an origin and destination is no worse than the cost on any other route. So this word flow should be cost. Okay. So there could be some routes that are more expensive, but they can't have any flow on them. Right? That's the rule. So let's check. Let's just see if the flow we had on the previous slide with the ward drop equilibrium. Right? So we already computed this. The cost from A to E to D to C was $1,400 per driver. Right? If we do this again with the cost from A to B to C, that involves link 1 and 2. And if we substitute in our numbers, we also have a cost of $1,400. So those pairs of drivers are happy. They're so far so good. But then we check the cost from A to B to D to C, right? And we compute this cost, and we get something that's $1,600, right? So this would not be a user equilibrium, because if you asked any of the drivers taking this route, would you prefer to switch routes? They would say, of course, I prefer to take either of these two routes. Both of these are faster, right? So this would not be a user equilibrium. Okay. What about system optimal flow? Well, how would we compute that? We call a set of flows a system optimal flow if you can't reduce the total flow in the network at all, right? So how do you compute total flow in the network? Well, you do it in the following way. You take the cost of a link, right, and then you multiply it by the total number of vehicles taking that link, by the flow of the vehicles on that link, right? So for example, link 1 had a certain cost on it, and that many vehicles was experiencing that cost, and so you take FE times the cost on that link, and then you sum it up for all the links in the network, and so this would be the formula you would use for this network, right? I didn't do it, it's some very large number, it doesn't really matter, but there is a system cost associated with this network, right? Okay, and again, as a traffic planner, you're probably more interested in system optimal flows, or at least trying to get to system optimal flows than you are in computing, than you are in ward drop. You would prefer to get as close to system optimal versus ward drop as possible. Okay, so that's kind of the general picture. That's where we stand. That's the mathematical setup. Any questions on that? Does that make sense? All right. So what we're going to do now is we're going to go through a series of sort of illustrative examples. And they're going to be like the simplest versions that we could imagine of these types of networks, right? So this is the game I like to play when I'm doing my research. I like to set up a mathematical problem and then find the simplest version of that problem I can imagine to try to understand kind of the fundamental things we have going on. Right? Okay, so suppose we have 1 unit of flow trying to travel from origin to destination. Why 1 unit? Well, it's just easier to think of this as just 1 unit of vehicles trying to get from O to D, right? You can think of this as 1,000 vehicles, 1,000,000 vehicles, whatever, but let's just say that's a 1 because it doesn't hurt the math to do that. So we're trying to route 1 unit of vehicles from origin to destination. Okay? And this is called Peugeot's network. It's a famous example in these routing games that demonstrates sort of the core theory that we're talking about. And suppose you have 2 choices. Every vehicle can either take this top link, and if they take the top link, their delay is 1, regardless of how many people are taking that top link. All right? But if they take this bottom link, their cost depends on how many people took that link, and it's just equal to the fraction that took that link. Right? So half the vehicles take the bottom round. Each of those vehicles will experience a delay of a half, and that's the cost for those half of the vehicles, right? All right, so let's think about what would happen if we were trying to understand what the ward drop equilibrium flow was. So the ward drop, again, means that every driver is happy with their choice and they won't switch, right? So if you look at this from the perspective of a single vehicle that's at the origin, trying to get to the destination, they have 2 choices. They can either take this route at the top, which has a cost of 1, right? Or they can take this route on the bottom, which has a cost of F, right? And F is always going to be less than or equal to 1, because there's only one unit of flow, right? So regardless of what F is, I'm always happy with the bottom lane. And in fact, if anybody takes the top lane, then there's strictly less than one people taking the bottom lane, and that's my preferred route. So I'll definitely go to the bottom lane, right? So if you do this and you think through this, that means that the word drop equilibrium looks like the following. It means that everybody is going to take the bottom route, right? And everybody's going to experience a cost of 1. So every single driver in the network experiences a cost of 1. And the total network cost, because there's one unit of flow experiencing that delay of 1, is 1. All right? Okay. So that's the user equilibrium, or the word drop equilibrium for this network. Is it a good flow? Could we have done better? If we could have kind of dictated where people went in this network, could we have done better than this cost of 1? Right, so how are we going to solve that? We're going to set up a mathematical problem to do that. We're going to solve for the social optimum in this problem. So we'll introduce a variable x. We'll assume that some x fraction of this one unit of vehicles takes the bottom route, and that the remaining 1 minus x fraction takes the top route, right? Okay, so x is a variable we're trying to solve for. Let's set up the total cost for the network. We're going to assume that, well, we're not assuming anything. We're now just trying to compute the total cost for this network. We have 1 minus x units of vehicles taking the top route. They each experience a cost of 1, right? And then we have x units of vehicles taking the bottom route, and they're going to experience a cost of x, right? Add these two numbers together. This is the total cost for everybody in the entire network. This is what the traffic planner, the social planner is interested in taking a look at, right? And if you compute this, you get some quadratic function, right? And then if you, so now we want to minimize this, right? So we want to minimize a quadratic function. We want to find the x that minimizes this problem. I'm lazy, so I went ahead and plotted it. So if you plot this function,